So, now the machines actually swinging in unison, that is coherently, I told you. So, let us consider the swing equations of two machines on a common base. We will consider only two machine case. So, for first one you can write H 1 upon pi f into d square delta 1 dt square is equal to say p I 1 minus p 1. This is equation 24 for the first machine. Now, for the second machine you can write H 2 upon pi f into d square delta 2 dt square is equal to p I 2 minus p 2, that is equation 25. Since the machine rotor swing in unison, that means I told you that they are in coherent group, that means their increase or decrease of the speed remains same. We can take then delta 1 is equal to delta 2 is equal to delta, this is equation 26. So, if you add this equation 24 and 25, so and substituting delta 1 is equal to delta 2 into delta, we will get, you add and substitute delta 1 is equal to delta 2 is equal to delta. Then you will get H eq divided by pi f into d square delta dt square is equal to p I minus p, this is equation 27. That means, where p I is equal to p I 1 plus p I 2, p is equal to p 1 plus p 2 and H eq actually is equal to H 1 plus H 2. Now, generally that H eq actually in general it will be G 1 machine into H 1 machine divided by G system plus G 2 machine into H 2 machine by G system, that is the H. Actually in general if you have G 1 H 1, then you have your this is machine rating and inertia. For second machine you have G 2 H 2 and third machine you have G 3 H 3 and so on. Then G 1 H 1 plus G 2 H 2 plus make it general G n H n divided by your system base G system, and that is actually H eq. So, H eq actually G 1 H 1 plus G 2 H 2 up to G n H n divided by G system. So, similarly here also we are putting the term machine, actually here also you can G 1 H 1 plus G 2 H 2, right, divided by the G system. So, this is the H equivalent, but if you take, if for example, if G 1 machine, G 2 machine and G system, if all the values are same, then basically it will be H 1 plus H 2. That means, when for two machines when they connected in parallel, right. So, their inertia should be added if they have equal rating, otherwise this way you have to convert. So, now we will come to the example. So, say the first example, a 60 hertz 4-pole turbo generator rated 100 MVA 13.8 kV has an inertia constant of 10 megajoule per MVA. You have to find out what? A, find the stored energy in the rotor at synchronous speed. B, if the input to the generator is suddenly raised to 60 megawatt for an electrical load of 50 megawatt, and find the rotor acceleration. And C, if the rotor acceleration calculated in part B, I mean here in part B here is maintained for 12 cycles, find the change in torque angle and the rotor speed in RPM at the end of this period. This is the problem you have to find out. So, that how we will do this? So, part A. So, store energy we know that G into H. G is given 100 MVA, H is 10 megajoule per MVA, it is given 10 megajoule per MVA it is given, and H is 100 MVA it is given. Therefore, stored energy 100 into 10, so 1000 megajoule. Now, in B, if the input to the generator is suddenly raised to 60 megawatt for an electrical load of 50 megawatt, find the rotor acceleration. Now, accelerating power P A is equal to P I minus P E. So, electrical power P is 50 megawatt and P I is that your what you call that if the input to the generator is suddenly raised to 60 megawatt to an electrical load, that is P I is 60 megawatt input. So, it is 60 minus 50 megawatt, that is 10 megawatt. So, accelerating power actually 10 megawatt. Now, we know M is equal to G H upon 180 F, that is we are putting megajoule second per electrical degree. So, GH is equal to 1000 into your 10 your one, it is actually 100. Here it is one, your Hg is actually 100. I have made a mistake, it is 100 into 10, but this answer is correct. 100 into 10 divided by 180 into 60, that is 5 by 54, that is megajoule second per electrical degree. Now, this m is known. Now, we know that m into d square delta upon dt square is equal to accelerating power P A. Therefore, 5 by 54 into d square delta dt square is equal to 10. So, that means d square delta dt square is equal to 10 into 54 by 5, 108 electrical degree per second square. This is the acceleration. This is the acceleration. So, 108 electrical degree per second, because d square delta by dt actually acceleration. So, alpha is equal to acceleration, say alpha we define the acceleration is equal to 108 electrical degree per second square. Now, part C it is mentioned that if the rotor acceleration calculated in part B is maintained for 12 cycles, find the change in torque angle and the rotor speed in RPM at the end of this period. So, 12 cycles means that is a 60 your 60 hertz system, it is 60 hertz system. So, 12 cycles means 12 by 60 is equal to 0.2 second. So, change in delta is equal to half alpha into delta t square, that is half that the acceleration into delta t square. So, half alpha is equal to your 108 electrical degree per second square into delta t square 0.2 square. So, delta actually 2.16 electrical degree, that is the change in the, it has been asked now that your find the change in torque angle. So, this is the change in torque angle. Now, this alpha is equal to 108 electrical degree per second square, this one we have to convert it to RPM, revolution per minute per second, the acceleration. How we will do it? Look, it is a simple arithmetic. 360 degree is equal to 1 revolution, 1 degree is equal to 1 upon 360 revolution, and 108 degree, that is whatever here, is equal to 108 by 360 revolution, but from where we got this RPM per second. So, that is your this one, that it is given no 108 electrical degree into second square. So, when you write like this, it is multiplied by 60, that means it is written no 1 upon second square. So, this one you can make it 1 upon second into second. So, this 1 second, right, this is your what you call 60 second is equal to 1 minute. Therefore, 1 second is equal to 1 by this simple arithmetic, right. So, because of this 1 second square, that is second square, that is second into second. So, that means second is equal to that 1 second is equal to, you put, if you put 1 upon 60 in the denominator, then 60 will go up. So, 60 into 108 upon 360 RPM per second. So, this way we define alpha is equal to your 18 RPM per second. If you simplify, it will be 18 RPM per second, because we have to find out that it is given no, and the rotor speed in RPM at the end of this period. So, this way you have to change the unit, that alpha unit, that will be RPM per second, you make it. So, 18 RPM per second, I mean this way we have to make it. If you do so, once again I hope this conversion you have understood, right, that how we have made this one. Now, therefore, rotor speed at the end of your 12 cycles, actually it is 120 f by p plus alpha into delta t. So, it is 120 into 60 by 4 plus 18 into 0.2, that is 1803.6 RPM, right. and that is why we make this unit, because it is alpha delta t, that is why 18 rpm per second, and that is why if it is rpm per second. So, second will cancel. So, unit will be rpm, and this is 120 f by p rpm, you know, and this is 1803.6 rpm. This is the answer. So, little bit be careful for your transforming the unit, and such that things will be all right. Next is that example 2. Suppose a 400 MVA synchronous machine, it is given H 1 is equal to 4.6 megajoule per MVA, and 1200 MVA machine has H 2 is equal to 3.0 megajoule per MVA. The two machines operate in parallel in a power plant. You have to find out HEQ relative to a 100 MVA base, that is system base is 100. So, the kinetic energy of the two machine is that K is equal to that your H 1 and G 1 H 1, this is your G 1 400 and H 1 4.6. So, 4.6 into 400, H 1 is given, plus your this H 2 is 3 and your G 2 is 1200. So, total is 5440 megajoule. So, this is your kinetic energy of the two machine. Now, that formula was given, that HEQ is equal to G 1 machine into H 1 machine upon G system, plus G 2 machine into H 2 machine upon G system. So, all the data given, G 1 machine 400 MVA, H 1 machine is equal to H 1, that is 4.6 megajoule per MVA. Then G 2 machine is equal to 1200 MVA and H 2 machine is equal to H 2, that is 3.0 megajoule per MVA, and G system is 100 MVA. That is on that you have to obtain. If you put everything together, it will become 54.4 megajoule per MVA. So, as a check, equivalent inertia relative to a 100 MVA base, the total kinetic energy was this one 5440. So, divide by system base. So, 5440 by your this thing, what you call that 100 MVA base. So, 5440 here actually it is 5440 divided by 100. I have by mistake I have made 1000, it is 100. So, it is 54.4 megajoule per MVA as a check. So, once again several times I have made repetition that all these calculations actually are done by me. So, if you find any calculation mistakes or any writing error or anything, I will appreciate if you let me know all this. So, example 3, that a 100 MVA 2 pole 50 Hertz generator has a moment of inertia 40 into 10 to the power 3 kg meter square. So, what is the energy stored in the rotor at the rated speed, and what is the what is the corresponding angular momentum, and you have to find out, determine the inertia constant h. These three things you have to make it. Now, synchronous speed n s is equal to 120 f by p, p is 2 pole. So, 3000 rpm. So, that will be actually your 3000 by 60 rps, right, revolution per second. The stored energy kinetic half j omega m square, it is a 2 pole machine. So, omega m electrical and omega m mechanical, electrical radian and mechanical radian both are same, because it is a 2 pole machine. Therefore, kinetic energy half j omega square. So, half it is j 40 into 10 to the power 3, and this is your omega, that is 2 pi your what you call that it is given rpm, that is 3000 by 60, that will be rps. So, 2 pi into 3000 by 60 square into 10 to the power minus 6 megajoule. So, that is actually coming 1974.43 megajoule. Similarly, that kinetic energy H is equal to kinetic energy stored divided by the MVA base. So, that is 1974.43 divided by 100. So, it is 19.7443 megajoule per MVA. Therefore, m is equal to j into omega m, this we know earlier, we have seen earlier also, that is 40 into 10 to the power 3 into this omega m into 10 to the power minus 6, here 10 to the power minus 6 is there. So, that is megajoule second per mechanical radian, and it is m is equal to 12.568 megajoule per second mechanical radian, but 2 pole machine. So, mechanical and electrical radian it is same. So, this is your this small example we have taken. Now, let us come to the power flow under steady state condition. So, we will take a short transmission line, we will assume that resistance is neglected. So, only your reactance is there for the transmission line. So, as resistance is neglected means the line is actually lossless line. So, for the purpose of basic understanding, we will consider a short lossless transmission line, and figure 2 is it is given that, right, and negligible resistance. There is no resistance in the line. For transmission line performance characteristic we have seen considering R, but here we will not consider R. That means, sending end real power and receiving end real power both will same, P s and P r will be same, because resistance is not there. So, the per phase sending end and receiving end voltages are V s and V r respectively. So, we wish to determine the real and reactive power at the sending end and at the receiving end, given that V s leads V r by an angle delta. This condition we have pre-assumed that V s actually sending end voltage leading receiving end voltage by an angle delta. So, on a per phase basis power at the sending end. So, your we know this previously we have studied for load flow studies also, that sending end power P s plus j q s, S s is equal to P s plus j q s is equal to V s I conjugate. So, this is equation 29. Now, from figure 2 that I is given by, I mean from figure this one, I is equal to V s minus V r divided by j x. So, I is equal to V s minus V r by j x, and if you take conjugate I conjugate, it will be V s conjugate minus V r conjugate divided by, as a conjugate. So, j x will become minus j x. So, this is equation 30. So, that here it is actually V s leading V r by an angle delta. So, from equation 29 and 30, that means here this I conjugate you substitute here, I conjugate you substitute here. If you do so, that S s is equal to V s into V s conjugate minus V r conjugate divided by minus j x. This is equation 31. Now, V r is equal to magnitude V r angle 0 degree. So, V r is equal to V r conjugate also will be V r, because angle is 0 degree. V s is equal to magnitude V s angle delta is equal to magnitude V s e to the power j delta, that we write. Now, all these things you substitute, all these things you put it here. If you do so, then you and simplify, you will get S s is equal to P s plus j q s is equal to magnitude V s magnitude V r upon x sin delta plus j in bracket magnitude V s square minus magnitude V s magnitude V r cosine delta upon x. That means, P s is equal to magnitude V s magnitude V r upon x sin delta, this is equation 32, and Q s is equal to magnitude V s square minus magnitude V s V r into cosine delta upon x. So, this is your what you call sending end power, real power and reactive power. Now, similarly, this in a similar way if you do so, then S r similarly at the receiving end we have S r is equal to P r plus j q r is equal to V r I conjugate. Similar way if you proceed, you will get P r is equal to V s V r upon x sin delta, and Q r you will get V s V r cos delta upon x minus V r square upon x. This is equation 36, but here our objective will be considering real power. So, therefore, for lossless transmission line P s is equal to P r is equal to magnitude V s magnitude V r upon x sin delta. This is equation 37. In a similar manner, the equation for steady state power delivered by a lossless synchronous machine, also it can be given as P is equal to say P t, then magnitude E g, then your magnitude V t upon x d sin delta. This is equation 38. So, where magnitude E g is the RMS internal voltage of the synchronous machine magnitude, V t is the RMS terminal voltage magnitude again of the synchronous machine, and x d is equal to direct axis reactance in bracket I have written or the synchronous reactance in a round rotor machine, and delta is equal to electrical power angle. So, P is equal to P t is equal to magnitude E t E g magnitude V t upon x d sin delta. Now, example your what you call example 4. So, the sending end and receiving end voltages of a 3-phase transmission line at a 200 megawatt load are equal at 230 or at 230 kV. That means, sending and receiving end voltage of a 3-phase transmission line at a 200 megawatt are equal, that is 230 kV. The per phase line impedance is J 14 ohm, that is R is neglected, reactance is taken. Calculate the maximum steady state power that can be transmitted over the line. So, magnitude V s V r, which earlier we have discussed, that we will go for per phase basis analysis. So, magnitude V s is equal to magnitude V r is equal to 230 upon root 3, that is 132.79 kV. Now, from equation 37, P r max is equal to P s max is equal to V s V r upon x, because in that case sin delta is equal to 1, the delta is equal to 90 degree, and V s is equal to V r magnitude, that means V r square upon x, that is 132.79 square upon 14. So, that is actually 1259.5 megawatt per phase. So, if it is a 3 phase, it is a 3 phase. So, it will be 3 into 12 1259.5 is equal to 3778.5 megawatt, that is 3 phase total. So, this example is a simple example. Next, you take the single line diagram of this figure, it is given here. Say the single line diagram of a system is shown in figure 3, that is, this is your figure 3. All the values are in per unit on a common base. The power delivered into bus 2, this is bus 2, an infinite bus having a voltage of 1 pu, this is infinite bus, voltage 1 angle 0 is given, and your what you call a bus 2 is 1 pu, that is that power delivered into bus 2 is 1 per unit at 0.8 power factor lagging. Obtain the power angle equation and the swing equation for the system, neglect all losses. So, this is the diagram is given, this is a generator and this is infinite bus. Now, before solving this problem, let us try to understand what is infinite bus. Generally, we know that infinite bus means voltage magnitude and its angle both will remain constant, but what does it mean for infinite bus? So, first we will try to see what is infinite bus, and then we will try to solve this problem, then things will be understandable for all of us, right. So, for example, that first let us define that how we define infinite bus. So, this is a generator is there and this is a power system network, it is given like this. This is a transmission network is given, its impedance is Z1, Z2, Z3, Z4, Z5, your Z6, Z7, and it is a large system here. With this whole transmission network is connected with a very large system, and this is a diagram I have taken, and this is a double circuit line. So, this is I have made mark it as a figure A, the general configuration. Now, for the purpose of analysis, the system of figure A, look, there is no link between this problem with this diagram. This is a take I have taken for purpose of explanation. So, for the purpose of analysis, the system of figure A may be reduced to the form of figure B. This is the form of figure B. This is equivalent has been made by using Thevenin equivalent of the transmission network external to the generator, right, or external to the machine and the adjacent transmission line. So, all these things and equivalent your Thevenin's equivalent has been made, and so this is generator will be there, this is the terminal voltage E t is there, and this is J d q is equal to R e plus J x e. This is the Thevenin equivalent we have made it, suppose it is we have made it, and this large system has been represented by a bus, says it is given E b, that capital E suffix b, and this is your we call this is infinite bus. Now, and this is a large system, it is a large system. So, because of the relative size of the system, I mean this is a large system, this is a large system. So, because of the relative size of the system to which the machine is supplying power, that means this is a machine, it is supplying power to a very large system, it is supplying a power to a very large system, right. The machine is dynamics associated to the machine will cause virtually no change in the voltage and frequency of the Thevenin's voltage E b. That means, compared to this system, the dynamics associated with the machine actually whatever may be the changes, the dynamics associated with the machine will cause virtually no change in the voltage and frequency of the Thevenin's voltage E b. That means, this system is a large, compared to that this generator is small, rating is small. Therefore, dynamics associated with that, if any changes is there, it will not cause any change to this voltage E b magnitude and its angle, it will remain unchanged, and such a voltage source of constant voltage and constant frequency is referred to as an infinite bus. So, this is your definition of infinite bus. So, I repeat that I mean concept should be clear. Suppose you have a generator and you have a heavy large system. So, you make one Thevenin equivalent, right, external to the your generator, this whole transmission Thevenin equivalent external to the generator, and that is J d q is equal to R e plus J e q, and this bus voltage here we make it as E b, that is the infinite bus voltage we call. And next is the dynamics of this system, I mean this system or this one compared to this one, actually this is a very large system compared to this, if there is a and it is not that large, it is small one. If any dynamics change associated with the machine, it will never affect this voltage and its frequency magnitude, your voltage magnitude and frequency. That is why this the Thevenin's voltage, such a voltage source of constant voltage and constant frequency is referred to as an infinite bus. So, that is the sometimes we call that what is infinite bus. So, this should be the definition of the infinite bus. Basically, it is a what you call is a Thevenin voltage E b, and system is so large that its dynamics cannot affect the this voltage magnitude and its angle. So, that is the definition of the infinite bus. So, because in this problem that infinite bus is there, that is why I thought I should explain you, and most of the numericals this that you always take that your 1 angle 0. So, this is bus 3 is given. So, this problem is generator thing is given J, your reactance is given J 0.25, transformer is J 0.15, and this is line 1 to 2 0.2, and this 3 I have made another bus bar is there, but we did not and your this side is J 0.1 J 0.2 same line, but total is 0.2. So, if you now if you your what you call make this equivalent circuit diagram, this generator voltage we can write magnitude E g angle delta, and this is J 2.5 sorry 0.25 and J 0.5. So, J 0.25 J 0.15 right, and this 1 to 2 it is J 0.2, and here it is 1 3 2 of J 0.2 and J 0.1, and this is infinite bus voltage right. So, we are making it as a 1 angle 0. So, this is equivalent impedance diagram of this network. So, this is your what you call the equivalent. From this one we have to solve that how we can do it. So, x eq can be taken as your these two you add and these two are in parallel. So, 0.1, 0.1, 0.2, 3 actually I have marked intentionally, but no fault, nothing is created. It is a double circuit line, but one more bus bar is created here. So, 0.1, 0.1, 0.2. So, 0.2 and 0.2 are in parallel. So, your x eq will be 0.25 plus 0.15 plus 0.2 into 0.2 upon 0.2 plus 0.2. So, 0.4. So, 0.50 per unit, and power factor is given 0.8 lagging. So, phi is equal to 36.87 degree lagging. Now, current into bus 2, actually if you read the problem, that the power delivered into bus 2 and infinite bus voltage is given 1 per unit, angle 0 is 1 per unit. That means, power delivered into bus 2 is 1 per unit and infinite bus voltage is also 1 angle 0 per unit and 0.8 power factor lagging. That means, current at bus 2 will be V I cos phi. So, I is equal to 1, this is input power, right, and this is your infinite bus voltage, and into 0.8 the power factor is given. So, V I cos phi is equal to 1, everything is power but lagging. So, minus 36.87, that is your 1.25 angle minus 36.87 degree. Thank you. Welcome.